So today's probably going to be the most applied lecture. Also, because today is probably the most important lecture also for the final assignment. So today we'll be talking about integer programming, invocable integer programming, and first use admit before it, because we're often not just using integers, but also linear variables, also binary. And this is where a lot of mathematical work also revolves around. So, first a small recap of last week. So last week, spoke about network problems. I put a few, I put a few animations online, so you can also view them back if I save the PowerPoint. Yeah, I don't want to post this to PowerPoint because they use PowerPoint instead of I prefer to post PDF. But they of course remove the animations. So I put the animations on the video. If you have any suggestions to that, let me know. So it's a trial, but I thought it was useful, so I'll keep on doing that and make animations like that. Also, there was a small error actually in the guide. I updated it, so of course the material for the exam course does include maximum flow and minimum cost. So that is changed now, so that is included in the exam material. I forgot to update it in the overview right here. So we spoke last week first of all about maybe the most important algorithm, or the most used one, which is the shortest path algorithm. Dijkstra is a prime example of that. It's a basic example. Of course, there are slightly more advanced versions which are slightly smarter way of going to the solution space. But Dijkstra is, let's say, the basis for almost all of them. Also, we looked at if we could also make that into a linear programming formulation and solve it, for example, through the simplest method, and we could. And of course, Dijkstra is much more efficient. However, for some problems, it could still be very interesting to be able to use an LP formulation for a shortest path. And we'll also see that with, I just showed a couple of other problems, like the minimum spanning tree, which is basically we need to connect every point in a network with each other through a single way, and we want to minimize the total length. Well, that's a minimum spanning tree, minimum total length, but a spanning tree in general means every element is connected in one way with every other element. We also showed later on that it was very important with the network simplex, because we need that to create the cycles and actually, let's say, apply a simplex method. So the spanning tree is very important, not just for this. Of course, if you look at a pure application, the Savada phone network is one example. But if you're talking like a Hyperloop network where you want to have everything connected, but only with a single line, then it's also interesting. Well, we also found that if we use an LP formulation to create a minimum spanning tree, that was easy enough. But we did need to constrain our variables first of all. We have to make sure everything doesn't go higher than 1, which is, let's say, the first step to go into a binary. We didn't quite have to set it as binary because of the corner point formulation. So because it's always in a corner point, it will always be 0 or 1. So in this case, we didn't yet have to worry about it. But we also found that we have to be aware, in this case, of subtools. So again, solver can be a bit more intelligent than we are. Well, intelligent might not be the right word, but it can find solutions which we did not intend. And the subtool is a big problem in that. And we also talk about that later. We'll also talk about maximum flow. Of course, you can again formulate an LP problem like that. So basically, it means every node should have a 0 net flow. So should have an inflow equaling the outflow. And there we try to maximize the flow into a certain node, out of a certain node. And that works quite well. But working better, especially if you want to expand the network and go towards commodity flows, is using augmented path, which we basically define paths throughout the network until we get our maximum capacity. And each of those paths then can be a variable instead of having the links as a variable, we can actually have the paths as a variable, reducing the number. But then if we go to a commodity flow, we actually have fewer options. And the people who do the airline planning course will see how that works. So basically, that's actually using an augmented path. Also, finally, we spoke about network simplex, which is ideal for minimum cost, but you can also do a maximum flow with that. And then we're actually applying the simplest method over networks. that requires, well, first of all, to use a spanning tree, so we need to create initial flows. Then we can actually, we need a spanning tree basically so we can short-circuit it using a non-basic, making a non-basic variable basic, and that will redirect the flow with a certain cost attached to that. And so that basically creates a cycle. Well, something required for that was the upper bound technique, which I shortly introduced, and that's basically allows us to, if we have a maximum flow, what we can do is we take the maximum flow, but then we actually add a reverse flow, which is then 0. But if a certain length is at its maximum flow, we basically reverse it, and then the reverse flow is 0, and that's non-basic. So that way we can actually create a link which has a flow and make that non-basic, and that will ensure that we actually have a spanning tree. Again, this doesn't work if we already have a cycle in the system. So today we'll be talking about binary and integer programming. So normally when we have linear programming, what we have is non-integer variables. So we just have continuous variables, usually with the constraint that they cannot be lower than 0, but they can be anything from 0 up to infinity with any unlimited number of digits behind the comma. What we did see, for example, especially with the transportation problem, but also with a lot of other problems, is that often we do end up with integer variables, integer values, but that's because our right-hand side, so our constraint values are integer. So even though if we don't set it as an integer, often we do end up with integer values simply because that's our right-hand side. With mixed integer programming, what we see is that actually some variables have to be defined as integer. That does complicate actually the way we solve it, so we have to take some special steps that we'll go into. Well, in integer programming, all variables are integer. So in a lot of cases, we don't actually, if we just run it, we'll get integer values, so then we're fine. But that doesn't always work. So in some cases, we really have to set a variable to integer and force it to be integer, and that means that there's a different solving method which we'll go into. Then in binary, of course, that limits it even more. That basically means a variable can be 0 or 1. Well, this causes some problems, but it also causes quite a lot of opportunities. So we can do quite a couple of smart things with our LP problem, which we couldn't have done without it. So one of the things we can do is when normally our constraints are hard, so we're not allowed to go over them. But what we can actually do is create a so-called soft constraint. And that basically means that we have, much like with the big M method, we have a high penalty associated with actually going over the limit of this constraint. So what we have in this case is a variable y, and basically we have let's say in this case we have a constraint with which is lower than or equal to a certain value. However, if it goes over, it can still be feasible by simply making the y in this case equal to 1. And if your y is equal to 1, it will always basically fulfill this requirement or fulfill it up to a certain level. So so the main reason for doing this is because often if you have a big problem and you run it and you only get the answer infeasible, then that doesn't tell you much. And at least by having this, you'll know why it's infeasible and you have some idea of where you have to start to look. Especially if you're applying, for example, if you have a gate planning software which is running at an airport, just getting the answer infeasible is not going to help you, but if it tells you, well, you don't have enough remote stands, for example, to cope with the capacity, then at least you know where you have to start solving the problem. However, of course, it can increase complexity a bit, but that's a limited method. What it also can do is we can actually have multiple objective functions. So normally, in an LP problem, we only have a single objective. We'll only get a single answer. However, what we can do is that we can put them all into one objective function, or we can add them up in an objective function, and then add weighting factors. And because of that, we can, for example, create a Pareto front where we can see actually the effect of trading off one objective for the other, but of course that requires running the model quite a large number of times. So one of the issues we have with integer programming, so one of the things we can do is simply relax the problem. So we have a certain number of variables which are integer, and what we can simply say is, okay, we'll just relax them. They can take any value and see what happens. So if we look in the left side, what we have an injected value which is equal to x2 minus x1 plus x2 lower equal to 2.5, x1 plus x2 lower equal to 3.5. So we have a non-integer right-hand side. What we can see happen is this is a feasible region. If we have an LP relaxed solution, so if we just solve this using the simplest method, we get the answer that x1 is 1.5 and x2 is 2. And what we can see is that then if we, so this is not a feasible solution because we need to have integer solutions. So what we can do there, well, is we have to then look at, okay, what is the closest one within this? What we usually do then, we'll talk about that more when we talk about branch and bound, is we set the x1, we set that to 1, or we set it to 2, and then we look at, okay, and then we run it again, and then we look what comes out. And then we'll find in this case that the optimum value is actually one of these, which has a value which is actually half that of the LP relaxed salt. So we call that so-called integrality gap, and that's basically how far our integer optimum solution from our LP relaxed solution. So in this case, let's see. In this case, the LP relaxed solution is 2. While actually our IP solution is actually 1. So actually it's a factor of half. This integrality gap is also very important when we try to solve problems like these. Here you can see another problem like that where we have x1 plus 5x2. 1 plus 10x2 is smaller equal to 20, lower equal to 2, so especially this causes a line with a very gentle, relatively gentle slope. If we take the LP relaxed solution, we end up with, 2 and 1.8. However, if we have a look at around it, then we end up here. So we can see we have an integrality gap, in this case, of 10 divided by 11. So in this case, we have 5 times 2 is 10. In this case, we have 10, 1.8, we get actually a certain gap. So we have to basically, first of all, solve the LP relaxed solution and then look around these neighbors. Well, there's a smarter way of doing that, which we'll talk about when we talk about branch and bound. A couple of the other things we can do by using especially binaries is that we can create certain special constraints. So one example is the either/or constraint, which basically means that either one of the constraints has to be withheld, but the other one can actually be ignored. So if you look at the top one, we have a sum of certain binary variables minus cj times yj has to be larger or equal to 0. Well, what does that mean? Well, if yj is 0, then this sum has to be equal to 0, otherwise it will be formulated. However, if yj is 1, then actually it can be equal to cj, so we actually have a if constraint. In this case, we have actually the opposite. So in this case, if yj is 0, then actually the sum of this can be equal to cj, but if yj is 1, then actually the sum of this has to be equal to 0. So this way we can actually have like a switch. So we can switch constraints on and off depending on the situation. K out of n, again, quite similar. Here we have a certain constraint. In this case, we have a large value. And if this is 1, then basically this constraint gets limited. So the C is so high, it's much higher than Vj or the sum. So it basically means that if this Yj, if this is 1, then basically this sum is not limited anymore. But what we do say that for a whole range of these constraints, that the sum of yj's has to be less than a certain number. So we can actually limit the number of constraints we can lift. This we can then put into a model. Also what we can have is n possible values. Again, we have a sum, and that can be equal to a sum of this, and I'll show you an example of this later on. So yj's are basically binaries. The sum of that, we can basically choose one of these values. That means that only a certain amount of these values can actually be 1. So these are quite complex constraints, but they allow us to let's say, make our model make a fixed selection. I'll have a nice example later on of impossible values. Another one, which is very nice to use, is a fixed charge. This one actually I forgot. There's also a yj in this case is of course also in our objective function. So yj also has a multiple in our objective function. Basically what it means is if we want to enable these options, xij in this case are options, or for example it can be the number of vehicles, it can be the amount of vehicles. And if we want to actually start utilizing that vehicles, we actually have to first incur a fixed charge. So in this case, if yj is 0, it means that none of these variables can be larger than 0. So it simply turns off this option. If yj is 1, then actually we can have a certain number of variables, so that's equal to bj, and if aij's are all 1s, then it simply says, okay, we can enable a certain amount of variables. So this is a so-called fixed charge. We can also show you some examples of this later on. And then, another very special one, an interesting one, is binary representation integer variables. And actually, much like the one we had before, so n possible values. And actually, by basically taking yi and then taking 2 to the power of I, that basically means that for y0 it's 1, for y1 it's 2, for y2 it's 4, 8, 16, etc. It means we can represent any integer number by a string of binary variables. So I'm not sure if you've done a lot with binary variables before, but basically the computer works with binaries. It's all zeros and ones. So if you have a 8-bit integer, you can go up to 256. So basically 2 to the power of 8. And any number integer value in your computer is actually represented by a row of binary variables. And in this way, you can actually mimic that. I'm going to show you an example of how this can be useful to actually do this in your constraint. So we can actually change an integer into a sum of binaries. More generic examples. In this case, we can have a system where we have an x1 and an x2. In this case, let's say they're both binary. In this case, only if x1 or x2 can be 1, but not both at the same time. So they can both be 0, x1 can be 1, x2 can be 1, but they cannot both be 1. So we have to pick one. The second one is actually so that's an OR constraint. The second one is actually an if constraint, and that basically says x2 can only be 1 if x1 is 1. So if x2 is 1, then 1 has to be lower or equal to 0, so that's not possible. So for x2 to be active, to be 1, actually this means that x2 has to always be smaller than x1. So again, we can force certain solutions. Then x1 or x2 is 1 in this case. So in this case, this is again the same like this, but we have a y1. However, if we enable y1, if y1 is 1, then actually they can both be 1. But in that case, only one of these can be 1, because here, if y1 is 0, either of these can be 1, but if y1 is 1, then actually only one of them can be. So this way, we can actually, again, let's say, eliminate certain combinations of variables. So you can make a choice. So the impossible values in this case, 3x1 plus 2x2, and in this case, it means it can either be 6, 12, or 18, but there cannot be anything in between. So the sum of these variables, 3x1 plus has to be either equal to 6, either to 12, or equal to 18. So it can actually have multiple sides. Actually, normally you have to say minus and then it's 0, but okay. Yeah, so these are typical things which we can do, and we can actually make our model make discrete choices. So hard versus soft constraints, as I said before, what we basically do is that we add a variable with a very large penalty in our objective function. So the solver will not like to take this penalty. However, if there's no other way to solve it, then it will. So in that case, it ensures that we always get a solution. But this constraint does not mean we get infeasible. And again, if you get the message infeasible by your solver, this doesn't tell you much. Some solvers are nice enough, like C++ is nice enough to tell you which constraint is giving you the infeasibility, which is already nice, but a lot of them won't. So especially LP solve will just simply not give you an answer. So the extra variable, which basically negates the constraint, so it has such a high factor, such a high negative factor, that basically it doesn't even matter what's beforehand. It will simply allow all the values to be free, and it's very important again to indicate where the infeasibility is. So this way you can easily track, okay, where is my issue. So if I'm having a gate planning, I don't have enough remote stands, then it will basically tell you, okay, we don't have enough of these remote stands. We need to actually properly solve this problem. A more practical example, I think most of you have done the DSE last year, maybe a few students from abroad have not, but it's basically the final third-year project. And there, basically how it started up is that Joris Melkers, once how he did it was he handed out papers, people had to write down their preferences, order them, and he'd collect all the papers, and he'd spend a day in his room with all sorts of piles and transferring things from one pile to another. I've actually been looking at modeling this process to see how inefficient it actually is, but it took a lot of time, and I went like, well, I think we can do this in a much better way. So most of you know we have to log into a website, and then you have to basically cross off columns and rows to indicate your preferences, and that's then put into a database. Well, then to allocate students, initially we started with basically a general assignment problem. So every group has to have a minimum and maximum number of students. And we tried to minimize the sum, but we found that some students only got to the last position because that meant that other students would be on the more primal position. We decided this was not very fair and very motivating for these students. So we made a couple of changes. So you can see at the top, the top constraint basically says that every student has to be assigned to a group. So Y is a student and J is a group, so every student must be assigned to a group. The next one said basically say that the number of students in the group has to be lower or equal to a certain maximum number, usually 10, or how large and equal to a certain minimum number, usually 9, so every group must be between 9 and 10 members. Then we have the objective value, we'll put it in the middle here, which actually contains two things. First of all, the sum of the choices times the score of each choice, plus let's say the maximum choice which is actually allocated. So it tries to minimize the maximum choice. So that's the YK in this case. So that's actually the maximum choice a student is allocated. Where we can see that back is actually in the constraint, which basically, what this one does is actually here we do actually a lookup. You can actually do it a slightly different way, but in this case I decided to do it like this, which does require programming to do this with Excel. It's too complex. But basically what we do is for every student, I look, okay, what is their first choice? If something is their first choice, it ends up in this constraint, and that means that these values can only be active if YK is actually 1. So if YK is 1, then these choices become available for the solver, and if it's not, then they're not. Then this one basically makes sure that if, for example, choice 2 is available, choice 1 must also be available. So it also basically, so you can't just have choice 4 and no choice 1, 2, and 3. So if choice 4 is active, then 1, 2, and 3 also have to be active. And then it tries to minimize, because of that, it tries to minimize the maximum choice. So you can also do this with, which was in the example by introducing an extra variable, but this actually creates a real integer programming problem because the YK is actually a decision variable. So first is Y1, is that 1, 0, 1, Y2 is 0, 1, Y3 is 0, 1, and that really creates let's say a problem which is good to solve branching bound, which we'll talk to in a moment. Another problem we had is that while most of the time it went okay, there were a couple of instances where there was a single girl in the group who did not really like it. So in that case, basically the dean, Jochen Hoekstra back then decided, okay, we want to make sure that there either has to be no girl in the group or at least 2, so to have a bit of a fair distribution. And in this case, we use a OR constraint in that. And this what we have is an IJ here, which is different from the YK. YJ, which basically means that if YJ is 0, then actually no girls have to be in groups. So this basically indicates that what Xij is that is a female. So for all the females in a group, if this is 0, then there can be no girls in the group. If this is 1, and then I'll switch this one to get rid of the here. Yeah. And if it actually is 1, then in that case, M is actually 2, and that means that in that case there has to be at least 2 girls in the group. So again, we give a binary choice to the solver. You can allow girls in the group, but then there have to be at least 2, or there can be no girls in the group. I actually have the same for males as well, but as the 80% of the guy, first people here are males, that's usually not a constraining constraint. Yeah. So I think this is where we start with, yeah. So the minimize and maximum constraint, what is that an example of? So if you log into response.eu, the code is there on the chalkboard. The minimize and maximum I indicated here with the green circles. What is that an example of? Fortunately, I've given off my indicator bar, so I have no idea of knowing how many of you are answering. Maybe I can. No, I can answer put in a counter. Is the software working? Good. Start the timer. Is everyone ready? Can I start the timer? You'll know if I can. So it's actually a fixed charge. The main thing with a fixed charge is that it has basically has a high penalty, or it has a fixed, well, it has a charge. It basically comes back in your objective function. So if it comes back in your objective function, it's either a fixed charge, or it's a soft constraint. Actually, it's more or less the same thing, except with a soft constraint, the penalty is very high. With a fixed charge, it's a bit more lax. It's a bit lower number. In this case, it's a fixed charge, so there's fixed cost in the objective for enabling a higher choice. Yeah. Okay, the females in the group, forcing the females in the group to be either 0 or 2. What is that an example of?
Zou je denken hoor, maar sowieso is het geen libero hoor.
Can I start the timer? Start the timer, it's 9 seconds. That's good. Yeah. So that's good. So at least there you were paying attention. So yeah, in either or constraint, so it's or if it's 0 or if it's at least 2. Yeah. That's good, at least you're looking at something at a time. So something, and this is something I want to give you mostly for the final assignment as well. It's always very important when you get a certain result for a model, especially if it's a more complex model, to actually have a good look at, okay, why am I getting this result? So this is actually an example of a graph from last spring DSE, so I'm guessing most of you actually took part in that. What you can see here is a line with the cumulative number of votes per group for a certain position. So it basically means, well, zero groups have, of course, are in the 0th position. And on first choice, you can see the light blue one is the most popular because it's on the first choice most of all. And then every time you add a choice, and basically accumulates until we get to 26. And 26, of course, if you go up to the 26 choice, then everyone has every assignment. So in this case, it goes up to just under 260, which was the total number of students. So this shows us a bit how popular different assignments are. It also indicates already how much the maximum choice will be in most cases. So you see that the green line is indicated with a red circle. You need at least to go up to the 5th choice to be able to fill that assignment. So in this case, you already know that's going to be 5. If you then look at the right, I have the number of students per assigned choice. You can see there we have students assigned to their 5th choice. You can really see it's needed because of that assignment, which is I have to go up to the 5th choice to be able to do that. So most of the time it works. Sometimes we also had that there were actually 2 assignments on that, and then if those are the same students, and actually we have to might go up to 6. But it's very important to look very careful is why am I getting this answer, and does it correspond with my data, and is that actually what I expect? So verifying is very important. So verification also in your final assignment is a very important part of what you're doing. So you can see in this case, well, about 68% got assigned their first choice. If we actually simply minimize the sum, so we leave out the minimax objective, that would actually be higher, but then you will actually see more students on like the 10, 11th position. So it's a much fairer thing. Something else nice to note, so you see indeed the dashed line here indicates, let's say, the minimum group size. I think that's right at 9. And here I actually see a dashed line, which is the average cumulative choice. You see all the lines basically wrapping around it, and this really indicates, okay, you can see how well it's distributed or not, and again, also allows to evaluate what students, what assignments do students like and what assignments do they not like. Last week I spoke, we ran a bit out of time, but I spoke about the traveling salesman problem, which is probably when it comes to network or integrate or let's say optimization is one of the classical big problems solved. Especially the Sweden problem, which they then finally solved, was a really massive undertaking. So what we have with the traveling salesman problem is that we have a number of destinations, and we can travel to and from any destination. So it's basically an unbounded network. So we don't have a limit to which node we can travel from. We can travel from any single node to any other node. And this makes it, from a network perspective, makes it massively big and very complex to actually solve. And often what we do is we don't even use linear programming techniques, but we actually go to other optimization methods. Though if you do it properly, you can actually also just use linear programming method, but you have to make sure that you limit your problem and also have a good initial solution. So in this case, they solve with a massive computational amount, but they also, so it's a massive computational effort. So one of the big things you have here is that if you want to pre-eliminate all the substrate, so I have a small formula there in the bottom. It might look small, but it basically means you have like gazillions of subtors which you need to eliminate. And so it's a ridiculous amount of subtors because of that, because the amount of subtors you can think of in theory here are massive. And that's why often, especially in this case, you simply use lazy constraints. You just run it, you solve it, you look if there's any subtors, and if you do see that, then you eliminate those. But probably end up like having to eliminate only a couple of hundred, which happen, but the rest you simply don't need. Because the subtor, let's say going from a normal to a top and then something like that is just not going to happen. So there's a lot of they're feasible, so that's why we need to do it in that way. So on how they actually solved it, they got an exact, so getting an answer here is not really a problem. So you could probably just go through it, take the nearest available and do like a DAX, go through it and you'll get a solution, but it's probably not the optimum. But to get the optimum solution and get it into an exact way and show that it's optimum is a really big task. And they solved this more or less using the branching bound method, which I'll show later on. Why this problem is so interesting is because it actually follows also a basis for the vehicle routing problem, which is maybe one of the, after the shortest path problem, it's probably one of the most used types of assignment problems we have. So vehicle routing. So it's basically usually it's a directed version. So the traveling salesman is actually a complete round tour. There's actually no beginning and no end. Everything is connected. You can go into either direction. So there's no preference there. And the virtual routing is usually directed. So it certainly specifies we go from here to here to here to here. So there's a start and there's an end. So there's actually a depot for the start and the end. The traveling salesman is a bit similar to what I have in hotels. And there can be multiple routes. So they can actually be multiple vehicles, or a vehicle can actually start and end multiple times, depending on the programming. And if we look at the kind of objectives we have there, we can throw out constraints. We can have all sorts of constraints on the number of routes, for example, the number of vehicles, the amount of payload. So how if you visit a certain number of customers and deliver packages, that the total sum of volume goes, maybe the weight may not exceed a certain amount. So even if you think about like the picnic cars, they have to deliver their foodstuffs. There's so much they can fit inside the vehicle, and then they optimize which vehicle does what to actually make sure you get an optimum delivery for that. Maximum range, especially if you're looking at an unmanned aerial vehicle, it has a limited range. So one time the fuel runs out, so you have to, let's say, limit the amount it can fly. Times, so there can also be time intervals or a limit on the time. So if you're doing vehicle routing, for example, now we have students looking at, for the United Nations, looking at their air fleet. How you organize that, and there you see that some airports you can only fly to during the day because there's no visual aids at the airport, so you can only fly during the daylight, so that also means the time for those locations is limited. And then also maybe you could pick up and drop off, so you pick up a package at one and deliver it at another, and also this requires special constraints. And these are all sorts of things, and there's lots more you can add to a vehicle routing problem. So if we look at so I'll just bombard you with mathematical formulation now. If we look at a typical vehicle routing problem, well, first of all, what we have is that we have an objective value, which is a certain cost associated with each vehicle. So xk in this case is a vehicle, so k stands for vehicle. So there's certain cost with utilizing a vehicle, so this is like a fixed charge. And then we have simply a summation of a certain link being associated with a certain vehicle. So ij is basically a link, k is the vehicle. So there's a certain cost with having a certain vehicle doing a certain link. And that can be, for example, distance-based, but it can be all sorts of other things. So the cost basically has, let's say, a certain value in there. So the first constraint, basically, each customer node must be visited exactly once by a vehicle. Actually says each node should be arrived at once. So because we have the I outside and the j inside the summation, it basically means that for a certain node I, that means outgoing is one. So if we have a certain node, then a vehicle must leave a vehicle, not a specific one, but a vehicle must leave that node exactly once. So the sum over all vehicles for all outgoing nodes has to be equal to 1. Second one basically says that these are basically the depot constraints. Basically, this makes that a vehicle can only leave the depot to a certain destination j if that vehicle is enabled. So xk is basically a binary indicating if a vehicle is active or not. It can actually also be a number of vehicles, but in this case, you'll run into a problem with later on constraints. But if this is a binary, if a certain vehicle is enabled, only then can the vehicle leave the depot and, of course, complete the route. Second one, same thing, but then arriving at the depot, actually this one you can usually just leave out because it won't actually do anything. So the next one is basically saying that if we have a certain vehicle arriving at a certain node, that same vehicle must also depart that node. That might sound very obviously logical, but for a model like this, if you don't have this, then you'll see vehicle A arriving and vehicle B departing. So again, you have to force it to have the same vehicle arrive and depart each node. And that's also why we don't have to add, to the first constraint, also add one for arriving, that each node must be arrived at once, but we only have to say departed once. If it's departed once, this one forces it also to arrive once. Then we have a slightly longer one. So So basically, this one, what it actually does is that if we have a time at a certain node, then the time at the next node must be equal to that time, or has to be smaller or equal to that time. So the sjk actually has to be moved to the other side. So basically, if we have time at node I, then the time at node j must be equal to the travel time, a certain time, traveling to yj, and there we actually have the k 1 minus xij, means that only if xijk is 1, then this constraint is actually valid. If it's not, then this gets a very, very high value, which actually releases the value for xjk. So this constraint only comes into play for that, and that's also why we need a smaller than or equal. We can't do this with inequality, because of course sjk comes back in a whole lot of constraint, but only one actually limits the lower value of it, and the rest will actually allow it to be small as it wants. Yeah, so this actually means that if we choose a certain route for a certain vehicle, then the time at the next node must be equal to the time of the previous node plus the travel time. If not, it releases it. Then we have the next one is basically, for example, for payload, but it can also be range, fuel, or time limit. So we're basically for each segment, if we choose to have a vehicle travel on a certain segment, then actually the sum of for that vehicle for all these segments that travel has to be at least less than a certain amount. So this can be distance, this can be time, it can be range, fuel, volume, all sorts of things. So it limits the sum of all the let's say all the ways a vehicle travels. And then the next one is basically where we can, because we have the SIK, so basically time at a certain node, we can also force that time at a certain node to be within a certain range. So we can say, okay, this has to be within this range, yeah. And of course, this is only if the node I is visited by vehicle K, then actually matters. If not, then SIK is not constrained, so it can take on any value it wants. So in that case, this SIK has no meaning. But it will get a value, but it has no meaning. So that's important to note. Have no meaning is not the same thing as have no opinion, by the way. But, yeah. And of course, in this case, xik, they basically have to be binaries in all the cases, and also xk have to be, they have to be integers. So we have to force xyk to be binary, otherwise, with a lot of these constraints, so especially this one, it will probably take a value which is something like a half, so it can actually negate all the constraints. So we have to really define it very. So if we actually look at this constraint, which basically says that the time of the node is equal or larger than the time at the previous node plus travel time, or if xijk is 0, it becomes irrelevant because it will always fulfill this. What type of constraint is this? Start timer. It's actually an either-or constraint, or to be more exact, it's an if constraint. So most of you, I'm guessing so most of you guessed. Most of you guessed wrong. It can't be the top one. But it's an either-or constraint, and basically means that if a certain vehicle travels on a certain route, then this is valid, and if it's not, then it's not valid. So it's an either-or constraint. Let's have a 10-minute break, and then I'll show you an example of what we can do in the